In this video, I'll be working through question 1 from the practice final. So, question 1 reads, explain how magnetic fields can store information in ferromagnetic material. So the first thing we have to remember is that ferromagnetic material has a history to it. What this means is that it's able to store magnetic information and remember that information as soon as you remove that applied field. How this works is we have our ferromagnetic material, and it's essentially made up of different domains. And in each of these individual domains, there are magnetic dipoles that are aligned with each other. Now, how this works is that the individual magnetic dipoles essentially come from the interactions between different atoms in this ferromagnetic material. So the magnetic fields applied from each individual atom on their neighbors helped preferentially line up the magnetic dipoles produced by each of these small components of the ferromagnetic material into certain alignments of domains. So we have different domains in the material, and all of them have a certain magnetic dipole to them in a certain direction. What happens when we apply an external field, be applied, is that these domains, the dipoles in these domains, will shift to try to align with the magnetic field that has been applied. Now, they won't shift exactly, but they'll all sort of kind of turn in towards the field so that the net magnetization on the ferromagnetic material is more preferentially in the direction of the applied field. So now we have a net magnetization. What happens when you remove this applied field is that now that the dipoles are lined up in this new configuration, the effect that they have on their neighbors is to preferentially stay in this new configuration. So the magnetic field by the one dipole on its neighbor will keep it situated in this one direction. So originally we had all these domains lined up in random directions with a random dipole magnetization. Once we apply our magnetic field, the magnetic moments will shift to be preferentially aligned with that applied field, and when we remove the field, we see the same thing. So I'll just draw the arrows as kind of an average in each domain here. But even when we remove that applied field, the magnetization that we have applied to this ferromagnetic material remains the same, and all the domains stay as they are. So in this way, we can answer the question of how magnetic fields can store information in ferromagnetic material, and say that if we apply an external magnetic field to a ferromagnetic material, this will preferentially align the magnetic dipoles of each individual domain with the field, and we're able to remember that field even after we have removed it from the ferromagnetic material. This can kind of also be seen in the magnetic hysteresis curve that we see here. We have the initial material at the center, and when we apply the magnetic field, we'll get some sort of magnetization, and at that point we'll have some sort of saturation, and in order to go completely the opposite direction, we have to apply an external field the other way in order to overcome the magnetization that has been stuck within this ferromagnetic material. So in short, to answer the question, we have an applied field that essentially causes a net magnetization in the ferromagnetic material, aligns the domains in a certain direction, and when we remove that magnetic field, the applied field, we obtain the same magnetization as when we had the field because the magnetic domains remain aligned in that direction.